Yo, what's up, Calc students? I got a new lesson for you. You guys are the first time that I'm going to be taking this lesson, which I used to condense into one day. I'm splitting it into two, where today's lesson was kind of part of Unit 2, Lesson 1. So I'm going to kind of add this to the end of Unit 1, which is the first half of what was one big lesson, and then the second half will start in Lesson 2. And in this lesson, we start talking about what calculus is really about. And calculus is really about how are things changing. It's called the math of change. We are going to introduce derivatives. We will never say the word derivative today. We'll start saying it in Unit 2. But we are going to start seeing what is a super important concept today. What tells you how things are changing in math? Now, if I ask you what is the change, how much did these numbers change, like from 3 to 15 or from 5 to 9? What is the change? And I hopefully you would say, well, you added 12. Yeah, and I would agree with you, like adding 12 is correct. But how do you get that 12 is you subtract to find like change. Subtraction shows like the distance between or the displacement between two numbers. So subtracting numbers shows us like a change from one to another. Subtracting numbers shows us the change. Okay, and I'd say, oh, adding 12 is more than adding 4, sure. But in mathematics, we usually don't just have a set of numbers. We do a lot actually in mathematics, but in a lot of the high school mathematics, we've been dealing with equations and functions, where it's not just two numbers, rather, it's an input that produces an output. It's an x and a y, where it's like, oh, if you started an x at 1, you have a y of 3. If you then go to an x of 7, you have a y of 15. And now we have the idea of like, well, we know our y's increased 15, or sorry, 12, but over the course of how many x's? And you could say, well, my x change was plus 6. So I increased 12 y's over 6 x's. When you divide these two numbers, all of a sudden we create this y's per x, 2 y's per 1x. It's like we simplify the expression to create one number, where this number can always be put over a 1. So I would say we are increasing 2 y's per x. Versus here, we have a y increase of 4, we have an x increase of 1, and we have this answer 4, or 4 over 1, or 4 y's per x. And all of a sudden, I would say, well, maybe this is more change. This is greater change. And then we talk about like what did we just do here? And as we found the slope. Average slopes, and this is like the first time we're going to talk about it, and we're going to talk about it over and over and over again. This is a key concept. Star this, underline it. Slopes are change. Remember this all year. If you want to figure out how things are changing, look at the slope. Let me just show you, like, and also provide some context. Let's say we have this function, and we have these points 1, 3, and 7, 15. Be like, okay, 1, 3, 7, 15. We can see those points existing on 1, 2, 3, 4, 5, 6, 7. This like graph that's created. We did the calculation of 15 minus 3 over 7 minus 1. We got that the y's are increasing by 2, the x's are increasing by 6. We get this 2. What is that visual? The visual is this slope of this line. This slope is 2. But we now have like an interpretation of what does that slope mean. Slopes equal change. We can say that on average, my function, what do you think, increased or decreased? We're going to say increase. Why do we say increase? Usually you'll understand that we say increase because the slope is positive. On average, my function increased 2 y's per x over the interval 1 to 7, where those are x's. Now, this is very important, this word average. It's average increase. If we went consistently 2 y's per x, we start at this point and we get to that point. However, we can see our function is not doing that. Our function is changing differently. Like we can see it's going up, it's flattening out, it's going down, it's decreasing, it's increasing. It looks like, you know, it's not obviously just increasing 2 y's per x, which is why we need this word average rate of change. It's on average how quickly it's changing. We then get to the point 2539, and we could see this steeper slope. We calculated this as 4. And I would say from this value, from this slope value, we have this statement. We'd say on average, my function increased 4 y's per x over the interval 2 to 3. Okay. Now let's look at 2 more points. 2560. So 2560. 1, 2, 3, 4, 5, 6, 0. We create this slope. Let's go ahead and calculate that slope. Well, from 5 to 0, I've decreased 5. If you did this idea of subtraction, we could say, oh, my y's decreased 5 as my x's increased by 4. This slope is negative 5/4. Cool. Now, a lot of us want to write a statement. On average, my function decreases 5 y's per 4 x's. But I don't actually like that statement because I like it to be comparable with the other rates of change that I found. So what I'm going to say is that this is 5/4 over 1. Or I'm going to write the statement, on average, the function, do you think it increases or decreases? So you'd say it decreases. Why? So that slope is negative. On average, my function decreased 5/4 of a y per x over the interval 2 to 6. This is the idea of a rate of change, a y's per x. But since we are talking about this interval 2 to 6, from 2 to 3, from 1 to 7, we can't say it is definitely increasing by this many y's per x over this interval. We have to say on average, because we can see my function is not always going up or going down. It's not always going down following this line, this rate of change. It's got to be an average rate of change. So an average rate of change is just a slope of what we call a secant. A secant line comes from geometry, where if you had a circle and you have a line cutting through a circle twice, we call that a secant line. We think of a secant line with functions as like a line just connecting 2 points. And we just use the slope formula. We can use the acronym AROC as the average rate of change, and we could say find how your y's changed, find how your x's change, get an m value, and you would say on average your function either increased or decreased based on the sign of this m, this many y's per x over the interval. Cool. So we pretty much did. Now, what if I give you an actual function, not just like made up points on a made up function, which this was just made up points on a made up function? What if I say, like, oh, the function is x squared? And we know what the graph looks like, and we can kind of see the graph. It looks like, that. But between x equals 1 and x equals 4, how do we find this slope? Well, we need the y coordinates. How do we find the y coordinates? You plug in the x coordinates. So we got f of 1 equals 1. We got f of 4 equals 16. Now we can see we increased 15 over 3. So if we want to do the calculations, we can. But hopefully you can see that, this is from 1 to 16, we're adding 15. From 1 to 3, we're adding 3. And you use 15 over 3 is 5. And great. And then providing the statement showing an understanding of slope, which many students have never done in the past. Provide the understanding of slope. You usually just like write down, here's the slope. But it actually means something. We would say, on average, my function is increasing. Why? Because that slope is positive. I can see my function is going up if we're looking from left to right. 5 y's per x over the interval 1 to 4. Cool. All right. And I would probably ask you to do the same for this and have the correct interpretation statement. So from 1 to 1/4, I subtract 3/4. From 1 to 4, I add 3. If you don't like to do that, you can use the formula that my average rate of change over my interval 1 to 4 is 1/4 minus 1. 4/4, so that's negative 3/4. And then 4 minus 1, which is just 3. How do we subtract? How do we divide fractions? Multiply by the reciprocal. Then I get this, negative 1/4. What is the interpretation? I would not like you to say we decrease 1 y per 4 x's. I'd like to say, on average, on a y's per x, makes it comparable. On average, j of x is decreasing. So it's from left to right going down, decreasing 1/4 of a y per x on the interval 1 to 4. Well, we can use trigonometry. G of 0 is 1. G of pi is negative 1. So I'm going down 2 over the course of pi units. So my slope is negative 2 over pi. I'd say on average, g of x is decreasing 2 over pi y's per x. 2 over pi, that's like 2 over 3. It's like 2/3. Think of that as like 0.666. Don't be worried about this 2 over pi being a weird number. And this is over the interval 0 to pi. Cool. I can give you a table of values. You can do the same thing. Average rate of change over the entire interval. I would just ask you for these 2 points. 8 goes to 0, down 8. 0 goes to 10. That's 4/5. I would say on average, this function is decreasing 4/5 of a y per x over the entire interval. Over what interval is the average rate of change equal to 3? Right here, 4 and 5. Over what interval is the function changing the fastest? So I'm probably trying to figure out when the rates of change are the most. So this is down 6 over 4, that's like 1.5. This is up 3 over 1, that's 3. This is down 1 over 2, that's a half. This is down 4 over 3, down 4 over 3. So it would be from 4 to 5, is what I would say. Don't know if it's a good question, but just as an example. Okay. Now let's say I went back here to x squared, and I not only said 1 to 4, and this number 5 is important because we're going to get it later. But if I said, let me give you, can you tell me the average rate of change from 1 to 4, from 2 to 3, from 7 to 12, from 5 to 9? Can you give me the average rate of change from negative 2 to negative 1? Can you give me the average rate of change of negative 2 to 0, et cetera, et cetera? I can have all these questions about these average rate changes. you would probably be a little bit annoyed at having to do the same thing over and over and over again. You'd have to plug in the x's, you get the y's. You'd have to then find the slope. You'd have to do the division. I mean, it's tedious, but would there be a different way? And there is a different way where we could somehow, once like knowing that we're going to be asked a lot of questions about like the average rate of change of x squared, we could kind of create a formula, a rate of change equation or formula. Cool. And I'm going to say, well, let's just pick an x point and let's pick a point that is h distance away from x to help me create the formula. Great, Mr. Messer. Well, what do we do with that? Well, let's find the y at these hypothetical points. Well, if I'm using x squared, this would be a y coordinate of x squared. We'd have like this point x squared. And then if this is x plus h, well, this must be x plus h squared. So we kind of have this point x plus h, and then like not x squared plus h squared. We know that's not true, but x plus h quantity squared. Cool. Well, what is the slope between these 2 points? Again, this is a hypothetical. X to x plus h. Well, we're going from x to x plus h. We can use the formula of subtracting our y's and then subtracting our x's. Does that make sense? Cool. Well, we have it. We have something. We have this average rate of change of x squared from x to a point h distance away from x. And we can make it look a little nicer, right? And if we wanted to, we could just stop here where the x's go away. X minus x. But I feel like I could do more. I could probably maybe simplify the top a little bit. Now, what is x plus h squared? Well, we probably need practice doing x plus h times x plus h. And we probably need to see it's x squared plus 2xh's plus h squared. Subtract x squared over h. Cool. And then, what else do we notice? Oh, look at that. The x squareds cancel. Cool. What else do we notice? Both of these have an h that I could potentially factor out. What do we notice now? Oh, I have an h that can be divided out of the top and bottom. And all of a sudden, I'm going to need more space. I have an average rate of change formula of x squared from x to a point h distance away from x to x plus h. Watch. Go back here. Let's go 1 to 4. And let's use our formula that the average rate of change of x squared from x to a point h distance away from x is 2x plus h. Well, let's say we're going from 1 to 4. I would say x is 1 and the distance is 3. Two times 1 plus 3. Bam. 5. Done. What about from 2 to 3? X is 2, h is 1. This is also going to be 5. That's interesting. X is 7. And then h would be 5. If x equals 7 and h is 5, I would go 14. 14 plus 5 is 19. Bam! 5 to 9. X is 5. H is 4. If x is 5 and h is 4, 14. I could get them so quick. Look, formulas. Great. that like an equation for an average for rate of change is nice if I have lots of different formulas. Isn't that cool? And what we just use is called the difference quotient. And the difference quotient is like, hey, do you want to create an equation for an average rate of change? Easy. Take 2 points, 1 point x, 1 point h distance away from x. If you have a point at x on a function, you have its y coordinate f of x. If you have a point x plus h on a function, you have an f of x plus h y coordinate. And you have this f of x plus h, y2, minus y1 f of x, and probably important to see the points just so you understand. And then here, this is x plus h, comma, f of x plus h. And then over, yes, it is x plus h minus x, but we realize that like this is the distance between them, h. So an average rate of change of a function from x to a point h distance away, you can say is always going to be this. Done, because the x's will always cancel. And we can use this if I'm giving you a lot of different average rate of change questions about the same thing. And we're going to just like practice doing it. But to be able to practice doing it, we need to understand what some distributions of things are. And I'm not sure if this is important, but we're going to look at like the average rate of change of just something like x cubed or something like x to the fourth. See, I'm going to say x cubed, what are all of the average rates of change over these intervals? And it might be, well, we'll talk about it in a second. So we need to know what x plus h cubed is as we are, okay, that's probably what I'm going to do. I'm going to say, come down here. If I wanted you to find the average rate of change formula for x cubed from x to x plus h, you would need x plus h cubed minus x cubed over h. We need to know what x plus h cubed is. Now, something that will help us is the binomial theorem or just Pascal's triangle, where we know that something to the 0 power is 1, something to the first power, nothing changes. So 1x plus 1h. Once we start squaring, we see things change. We have this x plus h times x plus h. And we get this x squared, xh, h squared, or x squared plus 2xh plus h squared, or 1x squared plus 2xh plus h squared. So we can see this 1, we can see this 1x plus 1h. Now we have 1x squared, 2xh, 1h squared. And let's multiply that by an x plus h. We probably won't do it in class. We probably won't do it here. But you can see, I mean, I can do it. Multiply by the x, multiply by the h. You'd get 1x squared, 1x cubed, plus 3x squared h's, plus 3xh squared, plus h cubed. And if we kept going, we'd be able to see, like for x plus h to the fourth, you'd get 1x to the fourth. We'd get 4 x cubed h's. We'd get 6 x squared h squareds. We'd get 4 x h cubes, and we get 1 h to the fourth. And we can go beyond. So you can kind of see like the x's increase by 1, the x squareds will increase by 1 while the h stays still, h is increased by 1. So we can turn this into x cubed plus 3x squared h plus 3xh squared plus h cubed minus x cubed over h. We could stop there if we wanted to, but we might as well simplify. The x cubes go away. I could factor out an h from every single thing. Just to help me, if we didn't simplify, we'd still get the answer. And all of a sudden, I get this equation. That the average rate of change of x cubed from x to a point h distance away is 3x squared plus 3xh plus h squared. Cool. Now, if we want to use our equation from for the average rate of change for all of these intervals, then bam, I would say x is 1, h is 3. And I'd be like, okay, cool. X is 1, h is 3, and I'd get 3 plus 9, 18, 19, 20, 21. Done! Here, x is -2, h is 3. So this will be 12. Plug in -2, I get -6 times 3, which is -18, and 9. So this is 3. Cool. -5 to 2. Okay, so x is -5. So that means I'd get 3 times 25, which is 75. 3 times -5 is -15. Ooh, h is 7. So -15 times 7. Which is -105. And then plus 49. So, okay. 75 minus 105 plus 49. So 75, that's 30, 40, no, 30 minus 30 plus, okay, 19. Done. Cool. Is that right? Seems like it. So I don't know. Is it right? How can I check? Well, hopefully you're thinking to yourself, Mr. Mester, why can't I just couldn't I just like plug in -5 and get like -125 and plug in 2 and get, so it should be a negative value. So what did I do wrong? H. Just 3xh. Well, let's see. 2 cubed is 8. 8. Oh, yeah, that's an increase. Never mind. So this is an increase of 133 over 7. What's 133 divided by 7? Look at that, our formula works. Okay, cool. We didn't even have to use a calculator. So x is 2, h is 1, and I could use my formula that I came up with, which is 3 times 4, 2 squared, 6 times 1 plus 1. So 12 plus 6 plus 1, which is 19. As well, very cool. Cool. Well, let's say I like gave you this x to the fourth, and I said, hey, give me the average rate of change from 1 to 4. What would you do? If you were given an option to plug in x's and use just like your equation or create a rate of change equation, which one would you choose? Ask everybody, and I hope you would say 1. And I would agree with you 1000% that sometimes getting a rate of change equation is not very helpful. It's cool, it's neat, but it seems like a lot of work, right? Like rate of change equations. Why would we bother doing it? Well, I'll tell you right now. starting next class, rate of change equations, super helpful, super useful once we talk about a different rate of change. Okay? So let's just do it both ways for 1 to 4. If I say f of x is x to the fourth, we'd say f of 1 is just 1, and then f of 4. What is 4 to the fourth? Ooh, 4, 16, 64. What's 64 times 4? 256? Or to the fourth? Nope, that's not it. 4 to the fourth. 256? Yeah, 256. All right, so we increased by 255 over 3. Let's do the math. 85 y's per x on average. Cool. Let's see if we get that 85 a different way. Well, let's use the average rate of change of x to the fourth from x to a point h distance away. We'd get x plus h to the fourth minus x to the fourth over h. And again, this is just y2 minus y1 over x2 minus x1, but with just generic points. I would get, simplifying, x to the fourth plus 4x cubed h's plus 8, 3, 1, 3, 3, 6, 6, x squared h squareds plus 4 x h cubes plus 1 h to the fourth minus x to the fourth over h. Goes away, goes away. Factor out an h or divide every term by an h. Divide the bottom by an h, divide the top by an h. Well, I'm going to divide every term by an h, and I get an equation. At the average rate of change of x to the fourth from x to a point h distance away is 4x cubed plus 6x squared h plus 4x h squared plus h cubed. Cool. When x is 1 and h is 3, when x is 1, I'll get 4 plus 6 times 3 plus 4 times 9 plus 27. 4 plus 18 plus 27 plus 27. 54 plus 22. What did I screw up on? X is 1, h is 3. 1, 6, 3, 9. Oh, 36. It's nice when, like, you know your mistake is not in the basics. 36 plus 27 is, let's do 36 plus 4 is 40. 18 plus 27, gosh, 30, 45, 45. 45 plus 40. There you go, 85. Got that same answer. Notice the formula, though, it's starting to get a little bit more complicated. It's not as easy as 2x plus h, right? But it can be used. And we can use it for these intervals as well, which is cool. And you're going to do it on your homework just for fun. But just letting you know that in reality, in your future, if I asked you to find an average rate of change, probably would want you to just plug in x's, get y's, and use this formula. However, formulas for rates of change exist. Sometimes they're extremely helpful, and sometimes they're extremely necessary. And you will see when they're extremely necessary starting in Unit 2. Okay? All right. Peace.